So we're going to prove the Guibart-Satterthwaite theorem. It's a relatively complicated proof. So I warn you ahead of time, it will require to focus a bit. But it's even more important than before. I mean, before there was a lot of blah blah and definitions, but now, I expect this proof to take between 45 minutes and 60. So if there's, I mean, we'll see how much it takes. Maybe you're just extremely fast, or maybe just you just give me go ahead, do it. But I will see. But anyway, the important thing is to remember what we assume about the voting rule that we have. So first of all, we're assuming that our voting rule for a given profile provides a single output. So this is different from what we said before. Now we're assuming the tie breaking happens and that's it. Then we want the rule to not be a dictatorship. And we're assuming every possible vote is legal. And we're assuming unanimity, which means that if all the voters put the same guy on the first position, this guy has to win. So this is so unanimity is our axiom, unrestricted domain is our axiom, and we're assuming that reporting truthful preferences is the dominant strategy, which means that whenever, if a voter could benefit by casting a different vote than his honest one, it has to be illegal, and it means it has to be impossible. Okay, so these are assumptions that we make. Lots of proofs, and we're starting with the proof of the Guibart-Satterthwaite theorem. And there will be a lot of somehow mental poker in here, because we will be switching between what's true and what's not true in the sense of what people's preferences are. And we're starting, so our setting is the set of candidates with ABC. We have at least 3. So for the theorem to be true, you need at least 3 candidates. We have this function, unanimous, non-manipulable, for a profile gives a single outcome. And we start with proving something that I call a shifting lemma. These slides are actually they're not the best for this thing, so maybe I will try to do it on the board. But what the lemma says that we'll actually see a lot of profiles like that. So if in profile V, there is some candidate who is a winner, and we form a new profile, V prime, where some guy B was shifted forward, then in this new profile, either the old guy is a winner, or the guy who was moved forward is a winner. So essentially by simply assuming unanimity and non-manipulability, we already get this relatively natural behavior. So let's see if I can show you the proof with the slide. Okay, so we will have here smaller chunks of proofs to deal with. So is there someone willing to be for this shifting lemma, it's only this slide, is someone willing to be my helper? Okay, you're willing to be the helper. Okay, very good. Okay, so I will do a proof by contradiction. So I'm assuming that in V prime, I have some other candidate who is a winner. So not A, not B. I call him C. So the fact that C is here involved in the shift is completely irrelevant. I simply have some other candidate. Now, imagine that voter V2 here, this actually happens to be the case here, that he prefers A to C. Okay? But here, A is a winner, whereas here, C is a winner, right? And all we did was shift B forward. So if here, he thought A is better than C, he still has to think that A is better than C in this profile.
Then he manipulates.
Huh?
Then he manipulates.
Yes, exactly. But now there's the mental poker part. If we assume that this is the truth, then he actually wishes to undo this shift and go back to V, where A is a winner. So if this is truth, and he prefers A to C, he would rather make A a winner. Since our rule is non-manipulable, this cannot be possible. So the other possibility is that C is better than A. But if C is better than A, again in V2 it has to be true in both profiles. Then here A is winning, here C is winning. So in this case, if this is the truth, and he thinks C is better than A, he can make a shift, and C becomes a winner. So essentially, simply because the rule is non-manipulable, the shifting lemma holds. So do you accept? Okay. I need 2 more people to say yes. Okay. Very good. Very good.
Can you please explain what non-manipulable is?
Yes. So essentially, I switched from saying truthful voting is a dominant strategy to saying non-manipulable. So I more or less view these things as equivalent. So when I say non-manipulable, I say that it is impossible for any voter to change his preference order in such a way that the result of the rule changes to something that he originally would have thought as better. So his original preferences are viewed as his true preferences. So he thinks that indeed, like in this case, this guy thinks A is best, B is second, C is second. If instead he reported a preference order CBA, and he got a better outcome with respect to his original order, we would say he has successfully manipulated. So a voting rule is non-manipulable if it's impossible to change a vote in such a way that you get a better response according to the original vote. Okay? So do you remember the Windows, Linux, Mac example? So that rule was manipulable because the Windows users could have shifted Mac forward and take point away from Linux, and if only one of them did it, he could have obtained a better outcome by changing a vote. So in a non-manipulable rule, this is impossible. So we want to show that if we assume that the rule is unanimous, non-manipulable, and of this form, so you always have one answer, then we will show that this is in fact a dictatorship. Yes. And we start, yes?
Question. So B, our V prime is where B is promoted.
Yes.
And it can be promoted even above A.
Yes. So that's why I said this is slightly a confusing slide, because I mean you can only show so much. But the thing that matters is that as you're shifting B, the relation between A and C does not change. Okay. Okay. So we're happy with this. This is an important.
We only want one property.
Yes. So far we only use non-manipulability. Yes. We will be, of course, using unanimity in other places. Okay. So this is actually a warm-up. Now the first step of the proof will go on. So we have a profile. So I'm assuming that here are some candidates, but I'm not writing them because this is somehow a mess. I'm simply taking a profile where a given candidate, so I'm focusing on B. B is somehow special for me right now. It's one of at least 3 candidates. And I'm claiming that in a non-manipulable rule, and unanimous in fact, in such a case, the winner cannot be B. This is pretty obvious, but of course it needs proving. I mean, it's not obvious at all, in fact, because we have to prove it from the 2 assumptions. But it's kind of intuitive that this should happen. Okay, so let's assume, for the sake of contradiction, that B is a winner in this election. Okay, so B is a winner in this election. Now I start making following moves. I take B and I shift. Sorry, it didn't make sense. I take some other candidate A and I just shift that candidate to the front. Okay? I can do it, why not? So here, for example, if I do it once, nothing changes. I do it again, nothing changes. I do it t-1 times, nothing changes. I do it for the tth time, and all of a sudden, the winner changes to A. And this has to happen because due to unanimity. Because eventually, if I do it for every vote, then it would be a unanimous vote where A is first. So by unanimity, eventually A becomes a winner, maybe on the last vote, but maybe earlier. Okay? Okay, I need another victim for this step. You? Yes, very good. So you accept this is fine. Okay? So far this is nice, nothing bad happened. So a step before, VT also preferred A to B, right? So before we made this shift, VT still thought A is better than B because B was last. Which meant that when we were looking at the profile of green and up to here, B is winning, but T can manipulate because he can shift A to the 4 and make A win. And we assume the rule is non-manipulable. So this is a contradiction. So is someone not actually? It's difficult to ask who doesn't understand because of course I understand. But so is there someone who wants more explanations? Is there someone who thinks that yes?
No. I just did not get it yet.
Sure.
I just need to
That's fine. Okay, let's just do it again. That's fine. Excuse me?
What to be conscious?
Okay, so I want to show that the winner in this election is not B. For the sake of contradiction, I'm assuming that it is B. Okay, so my assumption is that the winner is B. Now I choose some candidate in the profile and I shift him forward. I keep shifting him until I find a voter such that when I shift A, then the winner changes to A. So we know that B was originally a winner because we made that assumption. And by shifting lemma, we know that when we shift A, the only possibility is that A becomes a winner. And we know that eventually A has to become a winner because eventually we'll have a fully unanimous profile with A. So do you agree? And you agree as well. So consider this moment. So this is actually an important moment between T minus 1 and T. We know that if T shifts to the top position A, the winner becomes A. But before that, the winner is B, and A must be somewhere before B in this preference order, because B is last. So, because I'm shifting A forward, I'm making A winner. This means that in this particular case, this voter has ability to manipulate. And I have assumed that the rule is non-manipulable. So the assumption that the winner is B in this profile led me to a contradiction because it has showed a manipulable behavior is possible. Okay? Okay, good enough. Okay. So we know that we have shown that the winner is not B, and we're returning to you as the helper. Okay. Now what I do is the next step is shift B to the top position as long as it does not become a winner. So we're doing something similar as before. So I'm finding a voter R such that I have shifted B forward in all the votes, and I know that if I shifted B to the top here, then B would be a winner. And here, this is K because I just called it A, and these are just A1 through A whatever, just like that. So the winner is, so B is still not a winner. And I know that such guy R had to exist, such that if I pushed B forward, then B would be a winner by the very same principle as before, right? Actually, I need what's called verbal communication. So, yes. Okay. Now we make the final shift. So we shift B forward in this VR. Okay. I made the shift, and now the winner is B because that was exactly how VR was chosen. Right?
You're right.
Yes. Okay. So nothing special happened so far. But actually, this allows me to draw quite a lot of conclusions already. So first of all, as I told you, I'm looking for a dictator. And right now, here B is not winning, and R is ranking him last. Here, I only moved forward, and B became a winner. It's pretty darn likely that VR is my dictator. I have probably found my dictator already. Of course, I haven't proven it yet, but this is what I will be trying to do. So far, I can draw fewer conclusions. So for example, if I focus on the bottom voters, so R plus 1 down to N, I claim that if VI, so essentially if one of these voters changes a vote to another one, then B is still winning. So whatever these guys do, B is still winning. Why is that? Yeah, so it's actually a good answer. So often when I ask my students, like, what's the answer to here? The answer is, and what can I do? I have to wait. If he says, I don't know, it's great, because I can explain, and that's what I'm here for. So imagine that if I just made some random mess in these votes, and the winner changed to not be B. That would be an example of a manipulation. Because these guys originally think that B is worst, so if I was able to change a winner by just changing their votes, then that would be some way of changing these votes one by one that would have eventually showed a manipulation, a more preferred outcome. So if these guys could change the votes to not be, so for B not to be a winner, they could manipulate. And the rule is non-manipulable. Okay? So otherwise, some voter could lie in the profile. Okay? So this is actually important. So if there's someone who wants this to be explained again, yeah?
We are a manipulator, because like we change the outcome and he changes his opinion.
No. So depends. So it depends which of the profiles you view as honest. So if you view this profile as honest, so if V1 is the honest profile, and he shifted B forward, and B became a winner, this is not a manipulation, because he thought originally his truthful belief is that B is worst. And if he shifts B forward, then B becomes a winner, but according to his truthful opinion, this is not good. But of course, if you view this profile, if you view this profile as truth, then here, if he shifted B back, he could prevent him from winning, but again, this is against his best interest. Because, okay. So again, I guess everyone is assuming this is fine, or at least I'm assuming this is fine. Everyone is not willing to listen to it again. If we look at the top guys, V1 through VR, then again, none of these voters, so if a VI among these voters changes a vote to another one where B is first, B is still winning. And this is the same mental poker as before, because if they could somehow keep B ranked first, but make some mess here and prevent B from winning, then in this vote, in this profile where they made this mess, they would prefer to undo it and ensure that B becomes a winner. So they would have a manipulation. Okay? There's one thing that I'm somehow skipping over in here, and this is the fact that I keep speaking about a group of voters manipulating, but before we actually discussed a single voter only. So if we have this profile, we have V1, here is VR, and then the other ones. We're saying that B is ranked first, and we're saying, and here are the votes, such that if something changed here in any of the votes, we're saying if this prevented B from winning, then it's a manipulation because all of them would like to move back. But in fact, the way we think about it is, in the first vote, let's change the vote somehow. Okay? B is still a winner. Why not? I change another vote somehow, B is still a winner. I change yet another vote, and all of a sudden B stops being a winner. Then I know that this guy actually now has, in the changed profile, he has incentive to change another, to unchange his vote, because then B becomes a winner. Okay? So you're still satisfied? Yes.
Yeah. So
Okay.
I think so. Are we just trying to show one example when things doesn't hold?
Not exactly. So I will draw some. I will make. So first, notice that we started from a profile that simply had B at the bottom, and had whatever preferences here. So this somehow represents all profiles with B on the bottom. Now here we shifted. This is kind of all profiles where B was shifted to the first R1 positions, and this is a profile, all profiles where B was shifted to the top R positions. So this is somehow representing groups of profiles. So I'll be able to draw more general conclusions from this. But this is in 3 slides. Okay? So here, otherwise this voter would lie in the new profile. So, okay. Yeah?
So you're showing us some shifts shifts.
Yes?
And those shifts may or may not change the
Yes.
outcome. What I don't really understand is why you consider one's a manipulation and others are.
Okay, sure. Again, because this is so. By the way, I should have told you one thing ahead of starts. This is one of the most magical proofs that one can show in a class. And the magic of this proof is that we will be doing a lot of things, and every single step will be clear, and it actually looks like nothing in common with what we're really proving. So for the whole proof, it will be like, okay, fine, it's true, fine, where are we going? In the last minute, they'll be like, wow, it's proved. So this proof has this nature. So, okay, this is the warning. And the other thing is that there are two kinds of modifications of the votes. So there are modifications that I make, and for example, I consider this profile to be truthful, and now I make a shift of B, I create a new profile, and I'm saying that I change my focus, I'm saying that this is what the voters originally had thought. So imagine this is the truth that the voters believe. And now, assuming this is the truth that the voters believe, if they so essentially, so this was the shift I made, so it's an okay shift. But if they want to make the changes on their own, these guys, I'm saying that if they make changes that prevent B from winning, then that shows a case that they, in the modified by them profile, they could actually unmodify and manipulate.
So they are under suspect.
Excuse me?
They are under suspect. You can suspect.
Well, I'm simply, so this is somehow a mental game, because I'm assuming this is impossible. And from the fact that it's impossible for them to achieve some things, then it must be the case that whenever that guys 1 through R are ranking B first, B has to win. Okay? Okay, so I can do the same thing if I assume this profile V1 to be true. Again, these guys think B is the best. So if they could modify their votes in any way that B becomes a winner, they would have wanted to do it, and they could manipulate. This means that whatever they change here, they cannot make B winner. Okay? And the bottom guys here, on the other hand, they truthfully think B is worst. So if they could change their votes, well, so that B becomes a winner while keeping B last, then in the modified vote, if the modified vote would be seen as truthful, then they would, in that modified vote, they would want to undo and come back to the case where B is not a winner. Okay? So this is, and the conclusions, this was the first part of the proof, and the conclusions are as follows. If V1 through VR rank B first, then B is winning. So if these guys rank B first, then no matter what comes here, and no matter what comes here, B must win. So if we go back, we were looking at these two groups. So we said that here, as long as they keep B first, they can change whatever and B is still winning. And these guys, whatever they do, B is still winning. So the conclusion is that if the top R guys think B is best, B has to win. If bottom, so if bottom guys here think B is worst, then B has to lose. And this is all that we can conclude from here. And this is somehow it leads us to, again, it somehow shows that this has to be the dictator, but we still have to prove it. Okay, so this ends the first part of the first step. We're moving to step number 2. So the conclusion from step number 1 is staying with us. So if you're tired of being a victim, then I can get another one.
It's okay.
It's okay. But maybe someone wants to be. So essentially, if you want to ensure that you understand the proof, then join in. Otherwise, he will understand and he takes all your knowledge. Okay. Okay. So the second part. Now, we're starting with a profile where everyone thinks B is last, and the to-be dictator ranks K first. And what we will want to show is that if we have an election where everyone ranks B first, then the guy that is ranked first by R is winning. Okay, so we're making a step towards showing that this is a dictatorship. Okay, and now we will again make a bunch of steps that seemingly make no sense, and eventually there will be we will be able to show this is the case. Okay, so our first step is that we're shifting K to the top position in every vote. So K used to be first only one, he's somewhere around here, but we make a new profile where K is ranked first. And here obviously K has to be a winner because of unanimity, right? So we assume that whenever there is someone who is ranked first by everyone, he is the winner. So, okay, in this profile K wins. Now we shift B to the top in the first R-1 votes. We can do it, why not? So we have done it, and we claim that K is still a winner. Why? Yes, exactly. So essentially the only thing was, so we have this VR to VAR, they rank B last, so from first step we still have we still know that B is winning, K is winning, sorry. Okay, so now let's focus on this.
Could you repeat the last?
Huh?
Like we switched all these to the first?
Yes, so originally all B's were first, we shifted K to the top, and here we shifted B to the top in the first R.
Could become winner, but it cannot become winner because of the set.
Yes, but in fact, yes, exactly. Okay, so I actually didn't. So the argument was only half given. So if K was winning here, then by shifting B, the winners could be only K or B by the shifting lemma. But B has to be losing by the first step, so K is the winner. Yes. Okay, so we're focusing now on the profile V4, where we know K is the winner, and we create profile 5 by shifting B right behind K. Again, no winner change, or VR would want to lie. Is that clear? So if this was an origin, so again, actually I'm not sure if it's clear to me. Of course. So we have, yes. So here again, by shifting lemma, only B could have become a new winner. So if B was a winner here, but K was a winner here, then VR really would have preferred, if this was truth, he would prefer to have shifted him back and go back to the world of V4. Yes, okay. I guess, as you know the story from teachers, like one teacher comes to the other, I really don't understand this proof. And the other two, oh no, don't worry, I can explain it to you. No, I can explain as well, I don't understand it.
So I think you don't need shift and lemma here.
Excuse me?
You don't need shift and lemma here. Just manipulation.
Sure. Actually no, because you need the shifting lemma. Because if I shifted B here and C became a winner, then what conclusions do you draw?
Yeah, but
but K is first. Sure. Okay, fine. Okay. So we have in this profile V5, K is winning. Okay, we're perfectly happy. And now we're assuming, so far we only say we want to show that K is winning in V3. So now for the sake of contradiction, let's say that some G who is not K is winning in the profile V3. Okay, forget everything we've done so far, except that here in this profile K is winning and that we're assuming that G guy is winning here. And we'll do another set of silly steps that somehow will lead to the result. So by the way, if this proof really looks like a strange set of strange things that we're doing without make sense, that's because original papers by Gibbard and Satterthwaite were some 30, 50 pages long, and paper by Benoit is 3 pages long. So these 20 or 30 years of development in mathematics, it made the proof much shorter, but now it also looks a bit. So it's possible to present it, but there's a price. But it's very cute, and at the end you will be very impressed with the guy. Okay, so we're again starting from V3, and we're shifting B to the top in 1 through R-1. Okay, we have profile V6, so we have shifted B to the top here. Oh, and in the second to last in VR, so we also shifted B here. Okay, We have done it because no one forbids us from doing this. And by shifting lemma, since we only shifted B, the winner is either G as before or B because he was shifted. If G were winning in V6, then VR could shift B to the top and B would win. So does it make sense? If G, so let's say that G is winning here, and G, voter VR, certainly does not like G as much as he likes B, because B was shifted to the top position and K is not G, right?
But where we get to the G?
No, so we're simply assuming that the winner here is some guy G.
Oh.
He's not K and he's not B.
Okay.
So some other guy. And of course, we also know that G is not B because we have already shown before that if B is ranked last, then B is not winning. It's also even more. Okay, so here, G was somewhere in the vote here, but B passed him. And now we know that if we shift B a bit further, then B becomes a winner, because if V1 through VR rank B first, then B is winning. So we know that if G were winning in this profile, then VR would have a way to ensure a better outcome. Is that true? Okay, so first of all, imagine that we have shifted B forward here. Okay, then in step 1, we have shown that if V1 through VR rank B first, then B is winning. So okay, so we know that if we shift B forward, then definitely B is winning in this profile.
Yes.
We also know that G has to be ranked by R below B, because K is different from G, B is different from G, and K and B are on top of this vote, so G has to be below them. So if this is the truth, and G is still winning, then this guy can move B forward by 1 position and get a better outcome. So he can manipulate.
Yeah.
Right. So that's why we have a conclusion that here B had to be winning, because the only options were G and G couldn't have. So B is winning in this profile. That's nice. What do we do next? Well, we move to profile V5. So we shift K to the second best position among the voters V1 through VR1. So we make this shift, it's possible. We shift K to the top in the bottom part. So by these shifts, it's clear that we're obtaining profile V5, right? I have one nod, and I have somehow encouraging look from you. Yes? Sure. So essentially, the actions that I'm taking is shift K to the second best position in these votes V1 through VR, -1, and shift K to the top on the bottom part. And this way, I obtain my profile V5. Because all this profile in this whole story, all was done by shifting B and K. So whatever were the other preferences, they stayed the same. So okay, so I have another path of reaching profile V5. However, what happens, shifting K in V1 through VR -1 cannot change the result from B. So if you look at voters V1 through VR -1, they shifted K to the second but last position, and B was winning.
Yes.
So if this caused the winner to change, then they would have rather undo this shift and keep B as a winner, so that would be a manipulation. So it means that by shifting K here, so by making sure K is here, they couldn't have changed the winner from B to K. However, shifting K in VR +1 through Vn cannot change the result from B as well. And why is that? Let's see. So we're saying that shifting K to the top couldn't have changed the result. Well, again, that would be a manipulation.
Yeah.
Because here, imagine that this shift was already done, and now these guys are shifting K to the top position. If they succeeded, they get better outcome than they had, because it was B. So that's impossible. So the winner in V5, in fact, has to be, but actually it's K, but they're different, so it's a contradiction. Okay? Mm-hmm. So this is climax of step 2. So we have shown that if we have a vote where B is last ranked by everyone, then the guy ranked first by R is the winner. So we're pretty close to a dictatorship, not there just yet. Okay, so again, if there are questions, comments, if someone wants me to repeat the whole proof again, but for example, jumping on one leg and speaking with high pitch, then please don't do it, don't tell me to, but I could try. Of course, when I told that to my students, they said, yes, do it, and that was painful. So are we clear? Okay, then we have conclusion from step 2. If V1 through Vn rank B last, but Vr ranks K first, K wins. And now we're doing the final step. We have election where K is of course an arbitrary guy, different from B, but that's it. If K is first, we want K to be winning. So now we want to show that really there is a dictatorship here. Okay, so first of all, we shift B to the back in every vote. Okay, we're obtaining the same profile as in step 2. And of course, from step 2, we draw a conclusion that K is a winner, right? So we go back. By shifting lemma, it's only K or B that can be winning in this profile. Yeah, because to go back means just shifting B forward, or not shifting him at all. Okay, so if K is equal to B, that's a bit strange, but then it would mean we're done. Of course, this would somehow be impossible to do, so it couldn't have been, in fact. So K is different from B, and now comes the trick. We're doing the whole freaking proof from start, but for candidate C instead of B. We're redoing every single step we have done so far, we're doing for candidate C. Okay, this is possible, right? I chose B as an arbitrary guy. I'm doing this everything for candidate C. And what's the conclusion? Well, we discover, so this R that I claim to be dictator, we can call him somehow a pivotal voter. So we discover a new pivotal, new dictator VM if we do the same for C. Yeah, we'll find someone. Okay, so if C is ranked last, B is first on position V1 through VR, and then it's whoever. I just put A there. In fact, I'm putting A, B, and C here because I can only use 3 different candidates. So if this is such a situation, now B must be a winner because we have shown that whenever V1 through VR rank B first, then B is winning. So B is a winner here.
Sorry.
Yeah?
Shouldn't be there M instead of T?
M instead of R, or where?
Yeah, instead of R.
No, I chose R because this is the old R. This is the R for B. This is still the same R as here.
Okay.
We're not using this first one.
We're not yet using M, but we're going to use it right this minute. This second, in fact. Now, top choice of VM must be winning here as well, because we said that whenever, as in the previous profile, we said whenever B is ranked last, then the choice is of VR. Now here, whenever C is ranked last, then the choice is of VM. But B has to be winning. So we know that M has to be smaller than R. So we know that M has to be among these voters. Now, do the same trick again, but replace C and B. And by symmetry, you get R is smaller or equal to M. So essentially, we know that M is somewhere here. So maybe I can try to use the board. So what we did was that we have this profile. Let's say it's 1 R, there is B here, and then there's A, and there's C. Okay? And we said that M has to be somewhere here, right? Mm-hmm. So now let's put C here, A here, and B on the bottom. But now, what happens is that by the step 1 for candidate C, C has to be winning because guys 1 through M vote for C first. But it has to be that the voter that R ranks first has to be winning because B is ranked last in every vote. So we have our step 2. So again, this means that R in fact had to be here. Yes. So in fact, when we have redone our whole proof, but using C rather than B, we have discovered the same pivotal voter, the same candidate for dictatorship. That's nice. That's nice that the dictator doesn't change when we change our point of view. Life is not like that. But, so we know that we have discovered the same guy. And now, since M and R are equal, then we have shown that this means that here either K or B is winning. Here we know that either K or C is winning. Again, repeating the same step with C, right? Since either K or B is winning, and in the same profile either K or C is winning, well, clearly K is winning. Proof is done. We have shown.
So could you say, like, we realize that R is not bigger than M, then what do we do?
Yes.
Why is this arrow false?
Okay, this arrow?
Yeah.
Okay, so we have that M equals R.
Yes.
So now in this profile we had K, we shifted B back, and then we brought it back to show that K and B.
Yes.
But we can take C, shift him back, bring shift him forward, and now since this is true, since this is true also for C,
Okay.
then we had KB, now we have KC. And the only common point is K. So this is what I told you. For the whole proof, you have no idea what's going on. And then in the last conclusion, all of a sudden, there's a dictator and the proof is done. It's a spectacular way of telling students not to study mathematics. Okay. So are you convinced that the proof is true? So aside from possibly me trying to cheat a group of students and sneak in, but I have not, I hope that essentially every step is possible. To get a higher, the bird's eye view on the proof is actually very difficult. Because as I told you, this proof, this is 3 pages of text, distilled and rethought from 30 or 40 or 50 pages of text. So this was made to be presentable, but that's it. It's really, I mean, there's 20 years of effort between the original proof and this, so that's why it's really not so easy to glance how come someone actually came up with this proof. He came up with this proof because he had 10 other proofs to look at.
And this shifting them is due to him? Or
I don't know, actually. I saw, it was definitely proved in his paper, but I don't remember if he said that it was already used there or...
It looks like a very clear and simple...
Yes. But actually the original papers of Gibbard and Satterthwaite were actually somehow more general. They were dealing with more complicated notions, and that's why also they were more complicated. And so I'm not exactly sure if... I suspect Gibbard might have even had more general input for his data, so he couldn't have used something like a shifting lemma. But I'm not willing to bet my money on that. Okay. Come back to computer science. So actually, we've done it in 45 minutes. So this is exactly the right amount of time for this proof. We have different ways of changing the results. So what we discussed with this Gibbard-Satterthwaite theorem is strategic voting. And we know that it's possible in every vote, but there are things called control. I will explain them later. There's bribery, which everyone understands, and bribery means paying money to change votes, which is also known as campaign management and promotion. And there's a whole bunch of relations between these problems, which I will not really explain much in detail. But the bottom line is that we somehow like winner determination to be polynomial time computable. And maybe we would like this all hard, and all these problems actually turn out to be NP hard. And there was a moment of time when people thought it's a good thing. Because in the late 80s, early 90s, Bartoldi, Tuvey, and Trick, who actually essentially started this whole process of thinking about elections and algorithms and complexity together, they thought of something called complexity barrier approach. They said, if Gibbard-Satterthwaite theorem says that every voting rule is manipulable sometimes, then let's prove that manipulation is NP hard, and then obviously people will not manipulate. Okay, that was a bit idealistic. But it actually kept going. It was somehow, you can still read this in computational social choice papers. People still write it. It's silly, but they still do. I do my best to explain that this is wrong. And in fact, I will show you why we still care about these problems a bit later. This we can skip. And essentially we want to understand computational complexity of these problems, like strategic voting and bribery. And we will focus on this right now. So we're going back to computer science algorithms and things like that. So manipulation or strategic voting, what we have seen, that's a bit worse now. So the general setting is that we're given an election, we're given a preferred candidate, and the question is it possible to ensure that P is a winner, P's victory, by a given action specified in the problem? Okay? So for example, in the manipulation problem, for example, we want the green lady to be a winner. Green lady is a winner. We want the red guy to be a winner. And in fact, there are two manipulators, and we are asking if we can somehow place their votes in such a way that the red guy becomes a winner, of course, depending on a voting rule. And by Gilbert-Satterthwaite theorem, this may always be possible in some cases, but we want the complexity barrier. We want this to be NP-hard. And there was a bunch of proofs that, in fact, it's kind of interesting. If you have only a single guy who is manipulating, then computing his manipulation is actually polynomial time. As long as you have two, in most voting rules, you get NP-hardness. So even the basic form of coordination becomes NP-complete, and it doesn't matter because people do it anyway. However, what I want to focus on a little bit, because it's somehow nicer algorithmically, are bribery problems. And bribery is very simple. Yes?
Polynomial time in number of candidates, or
polynomial time in the size of the election. So number of candidates times the number of voters. I mean, you have to take both, because otherwise, okay, if you have a single voter to fill in, and you can somehow maybe do it in polynomial time with respect to the number of candidates, but only if you have enough preprocessed data. But generally, you need the size of the whole matrix. Okay, so in the bribery problem, you can have, every voter announces a price and says, I'm willing to do anything if you give me $1. Okay, that's a relatively cheap guy. Okay, this is how the problem is. So in the priced bribery, prices differ. Each time you pay a price, you can change a vote. This was actually in my PhD thesis. Very nice. In bribery without prices, everyone costs $1. So you can say that this is a model where somehow, for example, you got access to the votes and you get to change whichever votes you like, but you want to change as few of them as possible because you would get caught or something. Okay? Now, manipulation is in fact a special case of bribery, because if you set all the non-manipulators at high price and all manipulators at no price, then of course you have essentially a reduction from manipulation to dollar bribery. And of course the dollar bribery is a more general problem. Now I wanted to show some slides there, but in fact I think you probably need some waking up. So what we will do is something that is in the slides a bit later, but we will do an exercise. So we will consider the following setting. This will be plurality voting, or sometimes I refer to it as a naughty child problem. So in the voting setting, this will be actually relatively, okay, let's say we have C1, C2, C3, some candidates. We have here P. Now let's say that candidate P has obtained 3 votes. Okay, each vote is worth 1. Now candidate C somehow has many more votes. So he has 6 of them, each worth 1. Then there can be some other guy who has 5. There's actually no point for me to write 1 here, so I don't know why I'm doing it, but I am doing it. And let's say here's yet another one. So let's say we have this situation. So this is a very basic problem. This is plurality bribery. So plurality bribery. The voting rule is plurality, which means whoever gets more votes, whoever is ranked first more often, is the winner. So in this case, C1 is a winner because he has 6 votes, whereas C2 has 5, 2, and my preferred guy has 3. Okay? Now I want an algorithm that computes the optimal bribery that makes P a winner. So of course, essentially the only possible action is that I take one of the voters of the other guys, I vote him, and I move, so I move one vote from one of these guys to P. Sometimes I call it the naughty child problem or kindergarten problem, because kids in the kindergarten have built towers. All the kids were called for dessert, but the naughty child stayed, and he wants to win the highest tower contest, but he wants to steal as few blocks as possible, so he has to move so that his main competitor loses and he wins. So I'm sure someone can give me a polynomial time algorithm for this problem. I mean, it's pretty easy. So if you have an algorithm and you think it's easy, it's probably correct. Yeah? But just greedy is something that I give 0 on a test. So specify more. I mean, say more words than just, yes?
Maybe always take a vote from the one who's highest.
Exactly. This is the obvious thing to do. You just look at the biggest competitor, take the vote. Yeah, of course, this is whoever said just greedy, I'm sure he thought that. But I'm simply saying that you need to specify the algorithm. So it's in the same way, okay. There was a student who was attending topology class, and somehow topology is difficult. And the professor gave proof of a theorem, which was extremely long and complicated, no one understood. And I said, okay, now we have to do the other direction. He looked at, oh no, actually it's obvious. So of course all the students said, oh my God, I had no clue. No one could recreate this, no one. So of course the exam comes, it was an oral exam. The professor asked the student for the proof. He gives the first part, and the professor says, what about the other direction? So, oh, it's obvious. Oh yeah, actually you're right. When I'm asking for an algorithm, at least to my students on a test, if they just write it's easy, then it's not enough. Okay, but we're moving. So we're moving one vote here from the guy. Now it's 5-5. Break the tie anyway. So you move another vote, and you become a winner. So it's obviously correct, right? That was of course a teaser, because this was easy to show. This is more or less what you can. This is what would happen in real elections, but this is not fun algorithmically. So now, this is a real fun thing. Now imagine we have the same problem, again, either a naughty child or plurality elections, except that this is now a voting in a company, and people are weighted, which means that, let's say we have some candidates, P, and this guy has one vote, which is very high, and that's it. This guy has some smaller votes, and maybe a high vote. This guy has a lot of small votes. These guys, maybe something like this. This guy like this. And here, let's say our poor P guy, preferred guy, is at the bottom. So, for example, this could be maybe, let's make it like 6, 2, 2, maybe 6 as well. 1, 1, 1, 1, 1, 1, 1. This looks like 3, and 3, 2, and 5. Well, so this is our input now. Okay. And now, of course, we want P to become a winner. So for example, if I moved 6 here, so if I moved 6 here, I would have 6. Then this would be 6, this would be 1, 2, 3, 4, 5, 6, 7. So if I could still get 3, I would have 9 and I would be winner, right? But of course now the problem is, I want to become a winner in the fewest number of steps. Give me an algorithm. This is a great part, because for a long time I can just stay mute, nothing happens, I'm still doing my job. So of course, here Yes?
Two steps?
No, in this case, 2 steps, yes. No, but I want an algorithm, yes. So, of course, so also another thing I tell my students, if you're solving a difficult problem, it's a great idea to start with a wrong solution. Because if you just sit and stay mute, actually there is no progress. Unless there are interesting things happening in your head, and that could be the case. But it's actually quite good to start with a bad solution, and when you have a bad solution and you understand what's the problem, then you can actually come up with the good solution. So in fact, in my classes, when someone says, I have a solution, he comes to the board and it's wrong, he still gets positive points. Yeah?
So we have to do the swaps that
Yeah.
minimize the difference between the winner, whoever it is currently empty.
Mm-hmm. So in other words, so it's actually a difficult algorithm to specify if you were to specify it, but I could simplify it maybe slightly. Maybe that's what you think. You simply take, you look at the current winner, and take his most valuable vote.
Yeah. It can be that that you don't
Mhm.
need to take his vote, but you have some other valuable vote that
Okay.
you can shift, but
Mhm.
it would be
Okay, so what you okay, so first of all, let's do my algorithm because it's wrong. So
no. So what you say is wrong. No. Sorry.
yeah, but I want to explain why.
Okay, yeah.
So of course, if you had take the most valuable vote of a current winner, that's wrong because if this guy had lots of these ones, then it would be expensive to take them. Now, what you're saying is that we somehow have to balance between the current winner and the other wrong heuristic would be simply take the most valuable vote, and that would be again wrong because if all votes were equal to 1, then I could be breaking ties a bit wrong, or maybe all votes would be worth 100 and there would be a vote worth 101, but not from the right person, so I would still make a mistake. So what you're saying, I claim that your algorithm is underspecified. And the problem, it's actually not so easy to show why your algorithm is wrong, but it is. The problem is from the fact that if you're stealing, so this guy has currently the highest score, and probably you get most benefit by taking away from him. So you take this 6, but in fact there's a guy such that if you take this vote, you actually somehow the winner changes, and it's not clear how to compute the benefit that you get from stealing this vote, because it is not just whatever from this guy you got, because maybe you will actually end up taking this 5 and it will also not matter. So it's not so easy to show, but it's actually difficult to specify your algorithm, and it's and I claim it's not correct. Yeah.
Maybe you can take the chunks to yourself and keeping in mind the task to make all other candidates equal to each other.
It's step in a good direction.
Yeah.
Yeah.
Second best.
Take second best. But what if taking best is best?
The best is what is most valuable if it is taken from the winner.
Okay, so I suspect this is incorrect because I don't understand.
You take only valuable things from the winner.
Okay, you take from the winner.
Vital thing you take to yourself.
Yeah.
But if the winner doesn't have this valuable thing,
Mhm.
most valuable thing,
Right.
you're not taking it. You're choosing another candidate to take it who has the most valuable.
Oh, so you're simply saying take the most valuable item available.
If it's some from a person who is before you.
Oh, okay. So take the most valuable item from someone who is before you. Again, this would fail because if everyone before you has really low value votes, but there are guys below you who have very high value votes, but still lower than yours, you'd rather take from the guys behind you.
You take from the.
Yeah. Okay, so do you want to see the result? Okay. The result is actually tricky, but cute. So I need another picture for that. So if we have candidate C1, C2, C3, so on, P, they have some numbers of points all together. Let's say I'm here. This is somehow sorted from like this. Okay. So in fact, I'm using a bit of your equalizing idea. So I'm guessing that everyone will have less than t points. So I make a guess. Everyone will have less than t points. Let's say that here's one more guy. And I promise that I will have eventually more than t points. Okay, so certainly if there's a correct solution, then there is some value t, such that everyone has only up to t points, and I have at least t points. So I'm somehow assuming that it's enough for me to tie. Okay, clear? So anyone who is currently above, I have to steal their most valuable votes. So here I take this vote for me, this vote for me, this vote for me, and this is still above, so I take this for me. So anyone who is above my guessed threshold, I steal. If somehow I still end up below my threshold, then I steal the largest vote still available, and I keep doing that until I cross the threshold. Right? And in fact, if I chose the threshold right, then this must have been a correct strategy, because everyone got below the threshold at the lowest possible cost, and I got above the threshold at the lowest possible cost. This is, in fact, exactly the mixture of the two heuristics I told you about. So I'm first somehow stealing the most valuable from the winners, except that each of them could be a winner at some point of this stealing strategy, and then I'm stealing the most valuable votes available at all. So the only problem is how to choose the value of t. If I choose all possibilities, then this is an exponential time algorithm, because the numbers could be encoded in binary, and there could be exponentially many choices. But there's only polynomially many choices to try, because if I focus on a single candidate, I have to do the same thing for all of them, but let's say this candidate has this vote, then maybe a slightly bigger vote, another bigger vote, another vote, and so on. Then if I look at this guy, then actually, I always, whenever I look at a voter, I steal his most valuable vote. So either I will not steal from him, and the threshold then, from his point of view, would be this value, or I steal one vote, and this would be the threshold, or I steal two votes, and this is the threshold, and so on. These are the only reasonable thresholds from the point of view of this voter. So there are at most n values here, there are at most m candidates here, so I have n times m thresholds to try. Only polynomially many, I try each of them, the one that gives me lowest cost succeeds.
But we also could do binary search.
Not exactly, because it's actually not if you get a given threshold, the value of your function is just the number of votes you had to buy. The problem is that if you show a really low threshold, you will have a very high value because you have to put everyone below it. If you put a very high threshold, you have to buy a lot of votes because you have to pass it yourself. If you put a number in the middle, it will be the lowest. The minimum is somewhere there. So it's at the very least, the function at least has a shape like this. And in fact, maybe you could show that this is like that, but maybe it is like this. So it's not obvious that a binary search would work here. So is this at least that low threshold and high threshold give high values, but somewhere in the middle there's optimum? So it's at least not monotonic.
Okay.
Yeah. Okay. So of course here I have some advantage over you because this was actually a result from my PhD thesis. So I was prepared. Okay. But now the problem is that we'll actually go back to this plurality bribery in a short moment. So the next big topic somehow is what is the complexity of bribery in prominent voting rules? We already showed it for plurality for 2 cases. And the problem is, who cares? Because I told you that, I mean, would it ever occur to you that somehow there was a guy who had lots of money and he thought of bribing an election? He almost paid it. Oh my God, this is NP hard. I'm not doing it. So of course, anyone who's going to perform bribery in an election will simply just either find a heuristic or will just pay enough money that he'll pay more than needed, more than the minimum, and he'll do it. So apparently 20 years of research gone to hell. Fortunately not. This is actually a relatively recent, as of maybe, I don't know, more than 10 years, I guess. Maybe less than that. That we also started thinking there's actually much better motivation why we want to study such things as bribery or others in votes. The complexity barrier is not very meaningful, but we want to measure how well a candidate performs in a given election. So imagine that you have a basic election like this, the one that you've seen so many times. We're using Borda voting. And so the red candidate has 15 points and the orange candidate has 10 points. So would you agree that the red guy is about doing 50% better than the orange guy? Yes. Who else would agree? Okay, some guys. Okay. I somehow feel bad to do it, but let's now change the score for just increase 1. The guy now has 21 points and this guy has 16. Is he still doing 50% better? No. But nothing changed. It's the same bloody voting rule that puts them in the same order. If we use Copeland, and if we have election with somehow the graph like this, and the win gets 1 point, the tie gets half a point, the losing gets 0 points, then this guy has 3 points, this guy has 1, this has 1.5, 3.5 here. Is this guy 3 times as good as this one? Maybe, except if we change the win to 1, tie to 0, lose to 1, and they have 2 minus 2. And this just didn't make sense. Essentially, the problem, the mistake that I have done, and that I made you do, is that we were trying to use somehow ratios on things that are not scaled to the same thing. We can just add a constant to everything. The ratios change, but actually nothing changes in the performance. So it was, so essentially, if you try to compare scores in this way, it's completely meaningless. But you can use bribery problems to achieve how well someone did in an election compared to the other. So the amount of bribery, so let's say we're assuming everyone costs the same, or we're assuming some model of bribery. So the amount of changes needed in a vote to make a candidate win simply describe how well he did. And now if I need twice as many changes for one candidate than for the other, then I can say that this candidate that needs fewer changes is doing 2 times as well as the other one. Of course, you could say that it's not so necessary in single winner elections because looking at these points actually tells us something. But still, there are settings. If we look at committee elections, you will see that this is actually a big difference. Okay? And also, the amount of bribery needed to prevent a current winner from winning is measuring how closely the election was tied. This is in fact known as the margin of victory. So if the margin of victory of an election is low, then this is actually a strong motivation to actually to recount the ballots and to check if everything was intact. And there were elections where really few votes actually changed the result. Some of the presidential elections in the United States are point in case. Okay, so now if we want to study bribery, it's not nonsense, it's actually meaningful and useful. Okay, so the next set of slides was actually the plurality problem. So we know that unweighted, unpriced was our first example. It's polynomial time, and this was exactly the algorithm we have given. On the other hand, if not only we have weights like in the example, but we also have prices, then we actually have NP hardness of the problem. And I can show it quite easily. But I have to again use one of the NP complete problems that at least I haven't seen so far. So either you have to believe me, or I'm not sure what's the other option. So in the subset problem, our input is a set of numbers, S1 through Sn. So for example, like 1, 5, 6, 10, 12. And the question is there a subsequence that sums up to exactly half? So this is maybe partition sometimes called. So here the sum of these numbers is 34. So 12 plus 10 is 22. And then this is 12 together, 22 plus 12 is 34. Okay, and there is a solution. For example, this one is sum up to 17. And 17 is half of 34. Okay, and we can essentially now create a plurality election. We have two candidates. This was from the early days of my drawings. And let's say that one of them has all the votes that have, so each of the votes has the weight just like in the subset sum, but also has the price just like in the subset sum. So to get this 12 weight 12 vote, you have to pay 12. And you make your budget to be exactly 17, and clearly you can equalize them only if you find exactly a sequence that puts it in half. Okay. This is the moment when I expect somehow some sort of acclamation and support that this is correct. And yeah. Okay. So this was an easy reduction, and of course for these cases we have done the weighted unpriced, and okay and if you do priced unweighted, then essentially the same trick works. So you can try it on your own if you like. Okay, and now we can try to do bribery things with Borda. So this will be Borda dollar bribery. We have something called para-NP hardness, because these are some slides stolen from that were taken from slides I was for talks I was giving for parameterized complexity classes. I will explain what parameterized complexity is a bit later, but essentially here the point is that NP manipulation for Borda is already NP hard for 2 manipulators and 3 and 5 voters in total. So this means this was proved by a number of guys. But this means that in the dollar bribery problem, we're already hard for 5 voters and budget of 2, because we simply put, let's say, prices for these 3 voters that are not supposed to be manipulated to be very high, and the price for the others for 1, just like in one of these slides. So dollar bribery for Borda is actually difficult.
Maybe I lost something important.
Or maybe I was talking wrong.
In what input is it NP hard?
So essentially you have to encode every preference order as a sequence of names of the candidates. So you have 5 voters. Actually here you have 3 voters for which you have specified preference orders. So this is some polynomial number of candidates times 3.
So it's NP hard essentially in the number of candidates.
In this case, yes, because there's a constant number of voters. Yes. This is actually an extremely unusual case, but this holds for in this case. So essentially dollar bribery for Borda is NP hard. And we will not really look into that because the NP hardness proof is actually very, well, okay, it's not very hard, but it's technical and it's not as, you won't learn as much from it. But there's something that we call swap bribery. And this is a setting where, just like in the Dodgson election, you're allowed to make swaps of your candidate and the others. It's still NP hard, and it's still complicated and still not very useful. So instead of looking at that, we will look at, so swap bribery is also a special case of manipulation, but I will not explain why. We will instead look at a problem that I call shift bribery. And this is actually a very nice variant of bribery problems. Because we can only shift our preferred guy forward. And this is best shown on an example. So we're now focusing on the shift bribery problem. Yep.
So shift is different from swapping, we can move it as a...
Yes, so in swaps you could make any swaps. So for example, you could move, you want to make P a winner, but you swap C and D. In this case, you can only swap your guy. But in fact, I will show you a colorful definition right now. This is my new set of pictures. So imagine that this is election for the scariest monster. And you have the devil, a thing with big teeth, This is probably a vampire and Frankenstein. And we're using Borda voting. And so the devil has 7 points, vampire 3, Frankenstein 8, and the thing with big teeth has 6 points. Now my goal is I want the thing with big teeth, this thing to win. What I can do is I'm allowed to make actions of shifting this thing forward. So for example, in this case, I can shift him forward by 2 positions. And so each of these guys was shifted back. So each of them lose 1 point, but my thing got 2 points. So in the end, it is winning with everyone. So in particular, by passing the Frankenstein, it made his point decrease from 8 to 7, and its own score increased to 8. Okay, so the problem is that each shift, so for each voter, I have a price that tells me shifting this many positions costs this much. Okay, so this is the setting. And this is, so for example, I have right now a master's student who is implementing lots of algorithms for this problem. And he's, in fact, he's testing it on Formula 1. So for him, each vote is a race in Formula 1, just as we have shown before. And the price is actually different, the difference in times between two drivers. So how faster should they have been in a given race to pass a given number of drivers. So he's computing the lowest sum of times that a given driver had to be faster to become a world champion. And in fact, it's often slightly different from the actual ranking, official ranking of the drivers in the world championships. Okay, so I hope the problem that we're dealing with clear. And the setting is that for plurality, veto, and k approval rules, this is a polynomial time problem. It's quite obvious. If you think about plurality, then the only reasonable action for each vote is to just push my guy to the top. So if you play with a bit with this algorithmically, you find polynomial time solution. On the other hand, for Borda, this problem is NP complete. I could, but I will not show you the proof. If for some reason you think your life will be better than if I show this proof, you have to come tomorrow and you have to say you want to see this proof. Otherwise, I will not show it. So I somehow feel safe. But there's a 2 approximation for Borda.
What are you paying for and how much?
So I'm assuming, let's go back. If I have a shift like that, so in this vote, I have a number that tells me how much it costs to shift by 1 position, then I would only pass the devil, and how much I have to pay to shift 2 positions, so I would pass the devil and the Frankenstein. And of course, this has to be an increasing function.
But it doesn't have to be linear.
It doesn't have to be linear.
Depends.
It can be convex, it can be concave, it just has to be non-decreasing.
And it depends from voter to voter.
Yes, exactly. So the problem actually remains hard, NP hard, even if the function is linear. And it's NP hard if the function is just whenever I move the guy, it's already, I can just push him to the 4, it's still NP hard. Okay. So I have a 2 approximation algorithm. Okay, so this is the last thing we will do. I will show you this 2 approximation algorithm. It's also a bit mind twisting. So again, this is somehow like, so it's supposed, I can't say it will wake you up, but at least it should.
What is 2?
What is 2? It's a 2 approximation. So I will show an algorithm that in polynomial time finds a solution such that if it was possible to achieve, to make someone a winner at given cost, I will spend at least at most twice as much money, but I will achieve the result. So imagine like you're coming to your boss in a job and you're saying, you know, it's impossible to find the lowest price, but I spent twice as much as the lowest possible. I'm sure he would be happy. But in algorithms, this is actually, usually it's viewed as a good result if you have a 2 approximation. Okay, so this is what we are looking at. So first, more or less where the 2 approximation comes from. So if you have a vote, and let's say that you want the devil, who somehow changed now, because this is older set of slides, or actually, I'm wondering why okay, if somehow this was an effect of shifting the devil to this position, the position when you get, okay, and by the way, I'm not focusing on Borda, I'm now focusing on arbitrary scoring rule. So every position has its own score. So if I shifted the devil to pass the green lady so that she was moved back, he gained AI plus 1 minus AI points. So whatever she was getting minus what he was getting, he's now improved, but she lost exactly these points. Okay? And I claim that in the worst case, if there's some solution that gives me some number of points, if I get twice the number of points needed in that optimal solution, I'm definitely a winner. Okay? And imagine the situation that this is my worst opponent. He has this many points. And this is me. This is my number of points. In the best possible setting, for every point I gain, he loses the same number of points. So in the worst, in the best, most efficient bribery, if there's a way to get, by getting K points, to decrease him by K points as well, then I'm winning. But it's also, if I can get K points and another K points, I'm again winning. So if there's a solution that gets some, say, K points for my guy and makes him a winner, then every solution that gives him 2K points makes him a winner. So this is the intuition why this is a 2 approximation. But of course, things will be a bit more complicated. The way my algorithm works is, so here I'm using K for cost rather than points, sorry. I'm guessing the cost of the optimal bribery. So I'm somehow assuming that the costs are in unary numbers, so I don't worry about exponential time. I'm simply trying all possibilities. I'm guessing this cost, and I obtain, so here's a hidden dynamic programming algorithm that can find the best solution in the sense that I can obtain the highest number of points for spending a given amount of money. So here, again, you have to trust me. If you're interested in this dynamic program, then either ask afterwards or at the beginning of the next lecture. But in polynomial time, I can compute the highest number of points I can get for my devil at a given cost. And then I do it again for at most the same cost. This looks bloody stupid, but it helps the analysis a lot. In fact, it's possible, the algorithm stays at 2 approximation with just the first 2 steps. The proof is more involved and currently pointless because there's a better results already. But for the analysis, we will be doing this twice. Okay, this is the algorithm. Can we proceed? Remember, this is between you and the end.
What's point 3? Like, what we're guessing again? Because
so I'm guessing the cost of the optimal solution.
Yes.
I run a dynamic program that gives me most points at this possible cost. So as I told you, the best bribery could be that I'm lowering my opponent and increasing myself. However, maybe at the same cost I can increase myself higher, but without lowering him. So it's still, so it's not a solution, but
so at first you're putting your up, and then you're putting down.
So in fact, no. At first I'm putting myself up, and then I'm putting myself up again. But this is done in such a way that I can guarantee that this works. So maybe when you see the proof, it will be clearer. Because this is again a bit of a mind twister. Why this is done such a way, and the only reason why I have the same thing twice is because it's easier to analyze, but in fact it's not necessary. Okay. So now I will explain why this is a 2 approximation. Okay, so imagine that O is the optimal solution that gives P some T number of points. Okay, now in this picture we have voters, V1 through V5 in this case. The optimal solution will be marked with blue. So here in V1, my preferred guy is shifted by some number of positions, in V2 by more positions, and so on. This is what the picture gives. Okay? Okay, now my algorithm guesses a cost K, so the cost of this optimal solution, and finds a number of shifts in each vote that will spend this K amount of money, or maybe less, but let's say exactly K, and will get me a highest number of points. So let's say that this solution that my algorithm computed in the first step is marked by pink. And it's something, in some places I shift more, in some places I shift less, but I still spend both this solution cost k, because k was the cost of the optimal one. Okay, now I put them on top of each other, and so this strange other color that is lower in each case is the minimum of shifting in each vote. Okay, so these are shifts the minimum shift of the 2 in each vote, which gives some d points to p. Remember that the optimal solution was giving some t points to p. Okay, now there is a funny situation, because now, so imagine I have done only the shifts up to the minimum in each vote. Okay, imagine the situation. Of course, I cannot be at that situation because I don't know what's the minimum, because I don't know the optimal solution. But imagine I have just executed exactly the shifts that put me in this position that I still, that I'm right here. Okay, by continuing, just like the solution that I computed, if I continue this way, I will be getting at least t minus d points extra. Because I know that optimal solution was giving t points, my solution was giving the most points at the same cost. So if the optimal solution was giving t, then the S was giving at t or more. And here I have already obtained d points by this minimum shift. So I can, if I continue with the solution I computed, I will get t minus d extra points. Right? Sort of. Okay. So I see I just have to go on, and at some point you'll be happy that it finished. I think it's maybe 20 more minutes. I'm just kidding. Okay, but essentially the thing is that if I continue with my computed library, I get t minus d extra points for sure. However, if I went with the optimal solution, I can also make my guy win with t minus d points, which means that if from this point on, from this minimum points on, I get 2 times t minus d points, I will definitely be a winner, because it's a situation. I told you, whenever I can get twice the number of points than the optimal solution, I definitely win. So what I do is I continue just like in the computed solution I have. I get t minus d points, and I know that whatever was left from the optimal solution, it gives me a possibility of obtaining another t minus d points at the cost of at most k. And in the second step of the algorithm, I guess exactly how to continue this way. And I got my t minus d from the first, and now I get my second t minus d. And that's how I got twice the number of points needed for victory. And this concludes the proof. I see it would be overly optimistic to ask for a nod. I can only, so if someone you felt that you don't want to, this 2 approximation is nonsense that I don't follow, then I can cheer you up by saying that it's no longer the best result. Currently there exists a polynomial type approximation scheme. So it's not only a 2 approximation, but any approximation you request, I can provide. If you want 1.1 approximation, I can give you a polynomial time algorithm that does it. If you want 1.00001 approximation, it exists. And in fact, so I told you some of these slides I showed to students who were learning about fixed parameter tractability. In particular, I showed this 2 approximation, and a few months later I got an email with, oh, by the way, there's a better result now, because I proved it. So this is still unpublished, and I guess we'll be finishing here. And I have to think if we will still do a bit of single winner tomorrow in the first session, but certainly the second 2 sessions will be switching to committee elections. And it's all fun. Okay, thank you.